Yes, I think it's about the time to start this webinar. So welcome everyone to iclimabuilt webinar series. And today the topic is about structural glazing and functional coating for BIPV applications. And today we have two invited speakers, so Dr. Sophie and Dr. Bruno. And now I will give the floor to first Sophie Gledhill. And please start your presentation. Share your screen, please.
Hi, everyone. So you can see my screen. I just put it in presentation mode. So yeah, I'm Sophie Gledhill. I work at the Fraunhofer Institute for Solar Energy, which I'll tell you a bit more about in a minute. And prior to that, I come from a photovoltaic background. I worked at BP Solar in London, Great Britain. Then I went to the National Renewable Energy Laboratories in Denver, Colorado, before coming to Germany and working in Berlin at the Helmholtz Center. And I'll tell you a little bit more what I do at the Fraunhofer. The talk today is on structural glazing and functional coatings for building integrated photovoltaics, that's BIPV applications. So first of all, I'll introduce the Fraunhofer and the Fraunhofer ESA. Then I'll introduce what I do in the coatings group and our facilities. And then the main bulk of the talk is going to be on the morphocolor coating technology. So the morphocolor is a trademarked name for our colored coating technologies used mainly for PV and solar thermal systems. And in the picture, there's two examples of it, both installed in our institute, the Fraunhofer. There's a Stella there with green, blue, orange, and gray modules. And on the right-hand side is the new high efficiency technology building with the green solar cells installed. When I finish talking, I'll hand you over to my colleague, Bruno, who'll be looking at anti-glare structures for PV. Okay, so the Fraunhofer Society is a huge society. It focuses on technology for industry and is the research and development backbone for Germany's small and middle enterprises. So it's very applied research and it feeds directly into business and industry. It's got over 30,000 employees, 76 institutes all over Germany and some international. And most of the funding comes from industrial contracts and publicly funded projects, and 30% comes from the German government. Within the Fraunhofer, we are at the Fraunhofer Institute for Solar Energy Systems, otherwise what we call the ESA. It's the largest solar energy research institute in Europe, and it's based in South Germany in Freiburg. It covers all aspects from energy provision in the form of solar thermal energy, photovoltaic, synthetic fuels, energy usage, looking at energy efficiency in buildings, transport and industry, energy distribution in heating nets, electricity nets and smart grids, and energy storage, heat storage, batteries, and the hydrogen technology. I'm in the coatings group at the Fraunhofer ESA, and we feed into all applications developed in the Fraunhofer ESA. We offer solutions based on thin film coatings. And thin films, I am talking mainly about functional vacuum coatings on the scale of 10 nanometers to 1 micron thick. A large portion of our coatings affect the optical properties of our substrates. And I've just given a slide with some of the examples. For example, from the solar thermal power generation, we do highly absorbing receivers and highly reflecting mirrors. And we've had projects in the past on vacuum insulation glazing and optical switchable glazing. We also do different layers for PV, transparent PV electrodes or other contacts in the PV cell. And today we'll be looking at the colored PV modules in particular. So we have a wide range of applications, just a few are mentioned here. Our equipment is that we have these sputter machines. We've got a wide range of sputter machines, and our largest is shown in the picture. It's an industrial prototype sputter coater, and it can take substrates up to 1.5 by 4 meters squared, and you can sputter on a wide range of substrates, glass, metal, flexible films. If you know anything about sputtering, we can do DC, middle frequency. We've got a plasma etcher, and we've got exotic power suppliers like high PIMs. We can do co-sputtering. Not only do we do the film deposition, but we look at how the films age. So we have various climate chambers as accelerating tools, and then we characterize our films. The big thing is optical characterization. We've got Fourier spectrometry, but we also do microstructural analysis. We're equipped with an AFM, SEM, etc. We can sputter many materials. I've included a picture of the periodic table with the targets that we've had. So we can sputter. We have all these targets which we can sputter, and in addition to that, we can also sputter the respective oxides and nitrides by adding a reactive gas, oxygen or nitrogen, respectively. And then we adjust the relevant film properties by adjusting our film stacks, either the optics or the conductivity or the electronic levels, etc. And the services we offer, we do consulting in coating technology. So we look at process development, coating machine layout, and dimensioning. We look at optical simulation and design of the actual thin film system, and we do consulting in optical and electrical measurements. But now I want to talk about our morphocolor technology, which is used in the EU iclimabuilt project. And I'll begin by looking at what's the motivation. Why do we need this morphocolor color coatings? I start by looking at a report issued by the Fraunhofer ESA. And here it states that the policy in Germany is 100% renewable energy generation by 2045. And so that will require a PV capacity of 500 gigawatt peaks, which is equivalent to 2,500 million meters squared of PV. Currently, we have the present PV capacity of 50 gigawatt peaks. So that means that we need more than 400 gigawatt peaks of new installations in the next 22 years. Now, that constitutes an installation of 18 gigawatts peaks per year. If we look at the PV power generation per area, if you've got your PV modules sitting on your roof or in a field at ideal orientation, you're getting about 200 watts per meter squared. So 1 gigawatt constitutes the 5 million meters squared of PV. And for a facade where the PV is hanging vertically, not so optimally orientated, we get 130 watts per meter squared, constituting for a 1 gigawatts 8 million meters squared. And now there's a limited public acceptance for free field installations. That's when you've got your modules sitting in a large field. So most of this PV capacity needs to be installed on buildings. So BIPV, or building integrated PV, has huge potential for both roofs and facades, and it can have a substantial contribution to the CO2 reduction. But we need to motivate people to incorporate PV, and they'll incorporate it if people like it, or if on a building the heritage protection can be fulfilled. Just 2 pictures of black PV modules. So aesthetics is absolutely key for acceptance when you're installing on buildings. It needs to look attractive. On the other hand, aesthetics mustn't impair efficiency. The module is there functionally. It needs to produce energy. You don't want to be cutting much of your radiation to your module. And those are the 2 key aspects of morphocolor: aesthetics, but not at the cost of efficiency of the solar module. So this is just a marketing promotion. Where can you put the PV? And a colleague of mine takes IKEA as an example. IKEA, we've got these big blue facades. There's 55 huge IKEA stores in Germany, and with this facade area suitable for PV of approximately 270,000 meters squared. So the IKEA store was just a potential example, but what have we got already? We've already got our Morpho-Color PV module demonstrator with this lovely blue color, which is ready, is already developed and ready for manufacture and installation. We've also had several demonstrator buildings here in Germany, in Eppingen. In March this year, we had the installation of red terracotta panels integrated or hidden into a roof tiles at an old sports hill. And I show you the Fraunhofer building again with what we call our patina green eye-catching panels. And indeed, in the iclimabuilt project, we've had a small installation in Manresa in Spain at the laboratory. And you can see in the middle, we've got the two red panels hanging on the metallic frame of the laboratory there. Yeah, I mainly want to focus on building integration here, but there's also potential in vehicle integration. High performance in vehicles, of solar-powered vehicles, have been shown decades ago. And there's a picture of this Mercedes Solar Silver Arrow in 1985. And a colleague, Martin Heinrich, also in the project, has written a paper where you can see 10,000 kilometers per year can be solar-powered. But again, to integrate this in vehicles, you want to have good integration if you want to scale it up and deploy it. And there's been various projects putting modules into the car roof or the bonnet. And this is some recent work that was indeed even featured in the German newspapers, where the Morpho comes in to make either an attractive silver bonnet or various colors in the car roof to hide the PV modules. So what is needed for good integration with high efficiency? Colored modules and collectors must be bright, but with a muted color choice. Very key to our technology is that we must have good angular stability. That means that as you move around your module, you see the same color, or you see the desired color of your choice. And we need to retain the high efficiency of the black module, the uncoated module. More technically, that means that we don't want any absorption. And what that constitutes is we put our color coating on the rear side of our front glass, that we need a spectrally narrow reflectance. So only a small portion of the desired color is then reflected back to give the perceived color. And this requires minimal loss, but and a high color saturation. So our technology at the moment is that we have the colored layer integrated in the module on the rear side of the front glass. So we call our technology Morpho technology, and that's because it's based on the Morpho butterfly color concept. The Morpho butterfly is a Latin American butterfly. It's got a beautiful bright blue color. It's got good high angular tolerance to the color, but there's no transmission. You can't see through the butterfly. So the idea is to take your inspiration from the butterfly and you adapt it. So the color of the Morpho butterfly arises from interference within the periodic multi-layered ridges on the scales that cover the surface of their wings. Here we have a microscope picture of the butterfly wings. And if we zoom in further with an SEM, we can see the scales are composed of lamella. This is taken from a paper by Kinoshute. And he described the effects using a basic model consisting of infinitely thin and equally spaced lamella in air, which causes a Bragg reflection effect. Furthermore, the lamella have a limited width and a random distribution, randomly distributed vertical offset to the neighboring lamellar stack. This causes diffraction and results in an angular distribution of the reflecting light. So how do we get our narrow peak? The color we observe in the mortar butterfly is caused by the lamella, which have a separation distance of d, which equates to half lambda, where lambda is the designed wavelength, or the peak wavelength that's being reflected. Half lambda is known as the north harmonic. Lambda is the first harmonic. And if we take the 3/2, this is spacing, we have the second harmonic. By choosing the second harmonic in our interference stack, we get much narrower peak width. But that's at a cost. The narrow peak width is desirable for the PV because it's narrow width. But now we've got 2 unwanted additional peaks reflecting in the solar spectrum. At this point, it's important to note that the simple Bragg model does not describe the system correctly, since it assumes infinitely thin lamina. If you have layers of a defined thickness, then you start having vanishing peaks due to constructive interference. And here in our second order harmonic system, our first and third peaks are vanishing, and we're left with our main peak with a narrow width in the range of our solar spectrum. Now, lamella suspended in air are, of course, not a realistic structure for use in a PV system. As the morphostructure shall be integrated at the interface between our cover glass and encapsulants, more materials and more interfaces must be considered for an accurate modeling. And the thin film system that we actually use consists of high refractive index layers and low refractive index layers stacked up. So our real system is composed of a thin film sputtered silicon nitride as the low refractive index materials and titanium oxide as the high refractive index. The design is meant for high color saturation and angular stability. And we get the good coloring because we're using this higher harmonic reflection order. We have a higher average refractive index, and we have a suitable structured glass. So what does that mean? How does that affect? We're now looking at our mini module, and we're looking at the back side of the mini module, the rear side. And the glass is coated with our morpho color coating. And what we're seeing is the rear side of the wafer. And on the right-hand side, we have our black absorbing back sheet. If we flip our mini module around, now you can perceive the color. So everything is coated with our morpho color, but we only perceive the color difference on the absorbing bits, which is the wafer and the black back sheet. Of course, the colored solar module is not a new concept, and it is indeed, with this building integrated PV growing as a big area of great commercial interest. At the last PV-SEC, the big European solar cell company, in fact, there was a whole session on colored PV. And I just show you this results from a paper by a colleague, Christoph Cutter, who compared 2 other state-of-the-art colored technologies. He had firstly a colored encapsulant, which is a design where the colors are actually in the encapsulant material. And he compared that to a printed ceramic enamel design, which is also printed on the rear surface, and compared it to our morpho color coating. And basically, the color encapsulants and the printing raises the parasitic absorbance of the system and lowers the transmission to the solar cell. So that, the results on the right-hand graph, we have module efficiency. You get different efficiencies depending on the color of your module. So we have the red, the green, and the blue, and it's just comparing the 3 technologies. And the black line represents your reference with no color coating. And in all 3 cases, the morpho color technology clearly had the best efficient solar cells in comparison to 2 other color designs. So can it be produced economically? As I said before, we're sputtering. The technique is sputtering. You can see Andreas Wessels, our PhD student, loading the sputtering machine. It goes into the load lock, and it's a vacuum system. So once it's through the load lock, it's pumped down to 10 to the minus 6 millibar. We're now seeing our plasma ignited in our sputtering technology, and it goes under the targets. And we get the deposition of our silicon nitride titanium oxide film stack. It then comes out the load lock. Of course, everything's been speeded up. He lifts it up, and you can see it's transmission and transparent in transmittance. But when you put it on a dark absorbing background, we have this lovely green color with our selectively reflective reflectance. Yeah, so the conclusion, yes, sputtering is already, every glass window in Northern Europe has a low emissivity coating on. And although the morphocolor coating is thicker, it's definitely an upscalable manufacturable process. And we have a wide color palette. Basically, you can design whichever color you want. And we retain our high efficiencies. So we have excellent angular color stability. We've got, I'm showing on the graph, the modules that we presented a year ago at the EU PVSec in 2022. Yeah, they're well suited for large-scale production on glass coaters. And absolutely the rich color is achieved because we use the Fraunhofer matrix shingle interconnection. So we don't have any front contacts in this particular technology. So without the color coating, you have a very black cell, and with the color coating, you have a very homogeneous color. So a large portion of the development work has been to improve this angular stability. This has been carried out practically by looking at different glass structures and measuring using a spectrometer and a goniometer, or photographing at angles to visualize and quantify the angular color reflection. So starting with a structured glass, a 3D measurement using a laser microscope of the surface and height data was attained, as depicted. And the measured surface was used as an input for ray tracing scenery. The exact modeling is explained in the paper referenced here, and I don't want to go into details. It's not my work, but basically Andreas Wessels, our PhD student, using his ray tracing modules and calculates the simulated reflections and color as a function of angle. So what you're seeing in the graph on the y-axis is the angle of reflectance. On the x-axis, we have wavelengths, and the color constitutes the intensity. So we have a high peak at around 540, corresponding to the greeny color. And you can see with this glass measurement, we have a good angular distribution between 30 and minus 30, but when we get standing out at an angle of 60 to the perpendicular of the modules, we're going to perceive a much darker module. If we now introduce a second structure and compare by looking at the cross section, this second structure shows much steeper slopes, so we anticipate much stronger scattering. And this is exactly what we see in the model and what we measure. And by using this structure, the color is distributed across the whole angular range, resulting in the aimed homogeneous appearance. So here one can see that the peak spreads out for wider angles. And we can see this visually in the project. Here we have a color camera, which is used to photograph our improved demonstrator modules at different angles to the perpendicular, so plus and minus 80. And we really achieve a good color right out into almost 80 degrees. These modules have good efficiencies I've talked about before. The red, 94% of what a black module would be, 95% for the green, and 96% for the blue. So the Morphocolor has been patented and is a trademark protected. We have patents across Europe and Asia. And as I said, it's been trademarked. It's a trademark color name also across Europe and Asia and the United States. So in summary, the inspiration came from the Morpho butterfly. What we have is a modified Bragg stack using the second harmonic, and we achieve our saturated colors with our high angular stability. We have high efficiency due to this narrow spectral reflectance, and that's 90% of the power, more than 90% of the power is retained. We have our high angular stability, which is determined by the glass structuring. And this opens up many ways where we can build in and vehicle integration of PV using this Morpho color coating. So thanks for listening. Yeah, thanks to the many groups, the Fraunhofer ESA, who contributed this work, especially Thomas Kreuer, Benedikt Lasi, and Andreas Wessels. And I can take your questions. Many thanks.
Yeah, so you can, the audience, you can ask the question to Sophie, and by chatting, write the question on chatting or Q&A, or directly raise your hands up, and then I can unmute you. Is there any question from the audience? Well, maybe I can start. I'm wondering, does the type of the substrate affects on the efficiency of the PV or this type of Morpho color coating or not, if you change from glass to some other things?
Yeah, so the optics of the substrate. Yeah, so if you have Bruno were talking about anti-reflection coatings, of course, the optics of the substrate also affects the glass, but it does anyway. I mean, that's always the challenge in PV. The substrate that the coating on also has an influence. Yeah.
Okay. Thank you.
Yeah.
Anyone else?
Yeah, I have one question. Is it possible to buy the Morphocolor now, or?
So we've licensed. We have this license. I don't know whether you can still my slides. Yeah, there's so far a Swiss solar manufacturer, Megasol, has purchased the license, and they'll go into production. So it will be possible to purchase it soon.
Okay, thanks.
Okay, any more question? Otherwise, I'm going to move to a Bruno presentation. Okay. So now I give the floor to Bruno.
Yeah, hello everyone. Thank you, Sophie. Yeah, so I take over from here, and I'm gonna cover the last point of our agenda today. It is called Technological Developments for Anti-Glare Structure Glazing for PV Applications. And before that, I'd like to acknowledge my colleague, Janina Willman, who helped me preparing these slides. So as Sophie did, I'd like to also to present our group at Fraunhofer ISE. It is called Solar Building Envelopes. So we have kind of a coordinating role among the many groups we deal with the topic BIPV at the Institute. We ran for many years an accredited laboratory. It is called Tesla Solar Facades, and I left a link here for those interested in our experimental services. So our areas of research is the development of methods and for characterization and evaluation of BIPV and facade systems. This includes, for example, PV potential analysis, PV yield simulation, PV glare, which is the topic I'm going to talk about today, and daylight in buildings. We analyze the construction processes, what are the different actors that intervene in the different service phases of the construction process, what are the roles and what are the interfaces among different actors. And this help us to offer planning and design support services for different actors in the construction value chain. We offer know-how, for example, in terms of building regulations, but also experiments and simulation services. So I move directly into the topic of antiglare structure glazing for PV. These are the points I'm going to cover today: motivation, what are the evaluation methods, what are the technological developments at the moment, and then further aspects on the topic. So the motivation is clear. So the front glass of PV modules reflect sunlight, in many cases in a specular way, and this can cause glare. And we know this phenomenon from fully glazed facade. We have the example of our library here in Freiburg, which was built a few years ago, and it is a glazed facade, almost vertical. So after inauguration, there was a big problem due to the direct reflection going through a street where cars couldn't go any more because of the high reflection. So they had to come up with mitigation strategies after the inauguration. For example, putting extended this big shade from the roof to the bottom at some times during the year where this effect was more prominent. So this is a real problem for BIPV and less of a problem for other PV installations. So BIPV is usually installed on the facade, or in many cases it has a vertical tilt angle, and therefore the specular reflection goes into occupied areas in buildings and on the street, and of course is more visible than other types of PV installation. And Sophie mentioned the great challenge of installing 450 gigabytes in the following 22 years. So this side effect, this negative effect of PV installation, will be more prominent as the amount of installed capacity increases. So it is a good idea to look at it and try to find mitigation strategies. So the problem is clear. We have an intense specular reflection peak from the glass surface, And the measure to mitigate the problem is to use a structure glazing as front cover for BIPV. With a structure glazing, we widen the reflection peak. We spread the reflection distribution over a larger solid angle, and therefore is the overall intensity lower. These are some examples of structure glazing. We see here slightly structured glazing, for example, these grooves here, or moderately structured glazing like the pyramids or the pits, and more strongly structured glazing like this one, lasered. At the moment, there isn't any standard evaluation method to assess the anti-glare potential of structured glazing. So we have different possibilities. The first one is, of course, the visual inspection of samples. So we always like to take samples of structured glazing in our hand, put it under sunlight, and look at it from different view angles to understand how it behaves. But if we want a more quantitative analysis, we have to measure the samples, for example, by terms of its reflection distribution. There is a magnitude which is called bidirectional reflection distribution functions, and this can be measured with a photogoniometer, and this gives us the information about the scattering of the reflected light from the sample. These BRDFs consist of a large amount of data, so it is difficult to compare products based on that. So we need to come up with somehow of aggregated properties to be able to compare different design options. We can also use surface topography. I will talk about it in a minute, and of course, luminance images, either measured with a luminance camera or simulated in a ray tracing environment. So this is the first of the evaluation methods, what I mentioned before, bidirectional reflectance distribution functions. It is defined as the luminance perceived from a view position and view direction from the scattering of a sample, which has been illuminated with a glare source, and it has a illuminance on its surface, which belongs to the definition of the BRDF. The photogoniometer, or one of the photogoniometers we have at Fraunhofer is a three-dimensional scanning photogoniometer from the manufacturer PAP. And for this device, we illuminate a sample with a light source. In our case, it's a halogen lamp. And then we have a robotic arm with a V lambda silicon diode detector, which moves around the sample. So it moves actually through a virtual sphere of 1 meter radius, and it measures the light intensity at different positions around the sample. So if it's measuring in front of the sample with respect to the light source, it would be measuring a scattered reflection. If it's measuring behind the sample, it is measuring a scattered transmission. And then we can change the incident angle of the light source by rotating the sample in an axis which goes through the plane of the sample, or rotating the sample with respect to an axis normal to the sample. So BRDF looks like this one. So for a certain incident angle of light, we have a distribution of reflection in a hemisphere. This, which looks very homogeneous, corresponds to clear glazing or specular glazing. That means for a certain incident angle, this is 60 degrees, we only have one peak of reflection, which is very intense. And it is difficult to find this peak in this picture here, but if we look more closely, it's actually here. No? For 60 degrees outgoing angle, we find a peak, which reaches a value of 1,000 inverse stereo radians, which is, of course, a very glary or it would cause glare for sure. We work with a threshold for glare analysis of BRDF of 0.2 inverse stereo radians. Just to give a reference, although there is no widely accepted threshold for that. So if we take now the slightly structure glazing I mentioned before, these grooves, then the BRDF looks a little bit more different. So for 20 degrees incident angles, we have at 20 degrees a peak. This is scattered. It's not that small, as small as before, but we reach values of 1.6. This is already above the threshold. The problem is more prominent for higher incident angles. Here for 70 degrees, we reach values of 50 inverse stereo radians, and this is way above the threshold I mentioned before. If we move to moderately structured glazing, like the pyramids or the pits, we see that for 20 degrees, the specular peak has disappeared completely, and different peaks show up at different positions. Here we reach values of 0.6. This is already the same order of magnitude of the threshold I mentioned before. If we move to 70 degrees incident angles, the specular peak appears again, and then we reach values of 10 inverse stereo radians, and this is already a glare risk situation. So we have to move to a strongly structured glazing, like this one lasered here, to start seeing interesting things. So for 20 degrees, the specular peaks have disappeared completely. The maximum value somewhere else in the hemisphere is below the threshold. For 70 degrees, we see these peaks outside the specular region, and the maximum value 0.35, which is already the same order of magnitude as the threshold we've defined before. So we move to the second evaluation method, surface topography. So based on confocal microscopy, we can analyze the structure of different glazings. Here I just define them as S, SM, and SS. And what is interesting is to derive the surface angle distribution, because it gives us a feeling of the reflection behavior. If we have a narrow distribution, we'll see we can conclude that it has a specular reflection, so it can be glary. If it has a wide distribution, so different slopes are present in the structure, then we can assume that the reflection will be more diffuse. The third evaluation method is to use luminance maps. One way to do that is to measure directly samples of structure glazing with a camera for different view positions and view directions. Luminance is a photometric quantity which represents how we perceive brightness as humans. So it is widely used as a metric to assess glare in other applications. For example, glare in indoor environments from daylighting or from artificial lighting. Another possibility to generate luminance maps is through simulations. So we need a geometrical model of the scene we want to analyze of the sample. Then we can take the BRDF we measure with a photogoniometer. We need to translate the measured data into a format which can be processed by a simulation environment. In this case, we use tensor trees. And then, for example, using radiance or another ray tracing tool, we can again generate a luminance map of the scene. Luminance maps have the advantage that we are analyzing a particular application of the structure glazing. So the other evaluation methods I mentioned before deal with material properties. In this case, we can see how a certain material behaves in a particular application, for example, nearby an airport with a certain distribution of the PV modules and certain trajectories of the planes. We can really assess more in detail whether there's going to be a glare risk or not, and how we can mitigate it using structured glass technologies. So we move to the next point, technological development. What we have understand is that the state-of-the-art structured glazing, this which can be nowadays found in the market commercially, does not scatter the reflected light enough and leads to glare problems. And I show you some examples before of a slightly structured glazing or moderately structured glazing, and we saw that the threshold was exceed in many cases. So we are working at the institute in developing advanced structured glazing for anti-glare applications, and we are following a hybrid approach that combines laser texturing and wet chemical etching. Here in the diagram, we can see how the process works. And also the laser is making some holes into the glass, and then the etching is basically removing every round heel which is present in the glazing, and these round heels are actually producing a specular reflection, which is again causing glare. So here, just to give you a sense how these advanced technologies behave. Here it is compared with specular glazing. We have to make an effort again to find the peak, very intense peak of, in this case, of 100 stereo radians. For the structural glazing, we don't see any peak anymore. It is quite diffusely reflected everything, and the VRDF values are also very low. So for on structural glazing, so these technologies have the advantage to prevent glare, but it has a side effect which is also eccentricities, we are reducing the reflectance for high incidence
Bruno,
angles.
sorry to interrupt, but we are having some problems with your connection, I think. Maybe we are having some problems with the connection. Maybe if you take out your image, maybe we can continue without any problems. Just sorry.
No problem. Thank you for letting me know. I hope you understood what I said so far. Is better?
It was only the last slide that something, So just go ahead, please. Sorry.
Yeah. Okay. I wanted to mention that that as a side effect, structural glazing is reducing the overall reflectance of the front cover for PV for high incident, which means that the transmittance for these high incident angles will also be higher. It means when the sun, when the angle of incidence of the sun is high, we could have more electricity produced from the PV module when we have a front covered with a structural glazing, as when we have a specular glazing. So this is a positive side effect. There is another positive side effect. So here, a similar picture as Sophie. This corresponds to the color PV installation that has been carried out in Spain in the context of
Bruno. Sorry again. Still is at least for us, it's difficult to follow. Maybe you can one thing. The connection. Maybe you can leave the meeting and come back again. Maybe it improves. Sorry for that, but
the sound.
Yeah, it's the sound. It's the sound is it's getting difficult to follow. But I don't know if it is related to the connection.
Yeah.
So maybe you can go out the meeting and come back again and see if it is improving. Just
I checked the microphone. You hear me now?
Yeah, but it is like your
It's
voice is
same.
like interrupting.
Oh,
Yeah.
Okay. I will leave the meeting and come again.
Okay. Thanks. I'm sorry. Sorry about that, but Bruno will come back in few minutes, in a couple of minutes, and then I hope that the sound is better. In the meantime, if you have some questions for Sophie, that she's here, so please go ahead. So.
Hello. Do you hear me now?
Hello.
Yeah, it sounds better.
Yeah, better.
Okay, let's see.
Yeah,
I only
much
have
better.
2 slides left. So.
Yeah, maybe you can start one before, so that because
this one. Yeah.
Perfect.
So the point from this slide was the fact that we reached higher transmittance of the front glazing for PV if we use a structural glazing as if we use specular glazing. So this would be an additional advantage of the structural glazing. And now I wanted to mention another effect which has to do with aesthetics, and I wanted to refer to this picture from our installation in Manresa in Spain of our morpho color PV modules. So here we try to come up with a color which which is harmonious, can be architecturally integrated into this facade. and so we chose a red copper color. The morphocolor technology, as Sophie explains, needs structure glazing. So the substrate glazing has to have a certain rugosity. So it immediately has some anti-glare effects. So we can compare the anti-glare performance of the morphocolor modules with this other module, which is black. We can see it here. It is black and it has a specular glazing as a front cover. So we see here on the left-hand side, we can see the sky reflected in the module. Here we have a glare effect. I moved with the camera and could realize that from the morpho modules we didn't have any glare effect. So the structure glazing is providing a matte finishing BIPV modules, which combined with color technologies make PV invisible in the first place and offers design possibilities for architects and building designers. So this is my last slide. Just to summarize, I talked about the mitigation of glare by structure glazing, basically diffusing the reflection of sunlight. We saw that there isn't any standard method to evaluate the anti-glare protection of a structure glazing. So I presented different possibilities, and then we saw that the structure glazing improves the transmittance for high incidence, high angles of incidence, and this is relevant for PV installations on the facade. We always have high angles of incidence from the sun, and then we saw that this structure glazing enhanced the aesthetics of PV installations. And with this, I'm done with the presentation. I'm very sorry about the technical disturbances, and I'm happy to answer your questions if you have any.
Yes, the audience, if you have question. Oh, Sophie.
So the structuring on the glass, Bruno, looks very harsh with the lasering and the etching. Does it have any effects on the mechanics of the glass or the soiling of the glass? Has that been investigated?
The mechanics, I cannot answer that, but the soiling is an issue, of course, that we are investigating. So as soon as you have terrain, you have holes in the glass, and this is placed outside for many years. Of course, dirt will be deposited in these holes, and this will affect the PV efficiency and also the anti-glare properties of the glazing. So we are actually investigating ways to mitigate this effect based on cleaning technologies, but also anti-soiling surface treatments.
Any more question?
Yeah, I have similar one to what I asked to Sophie. So these PV modules with a structure from glazing are already available in the market?
So the ones which are available, so the anti-glare technologies actually come from the anti-reflection technologies. So basically preventing that the front glazing of PV modules reflect sunlight, therefore increasing the transmittance and the efficiency modules. So there structures which were commercially available. These are the ones I showed at the beginning. slight structure, moderate. Usually, you order PV modules you can choose which front cover you want on them. These ones we realize that are not suitable for anti-glare in many applications. If we think new technologies, there are now some manufacturers which are offering laser structure glazing, and of course the latest technological improvements are still into development phase. They are not commercially available yet.
Okay. Any more question from the audience? Okay, so I would like to thank you very much, both Sophie and Bruno, for this nice talk. And I hope you all learn about the information of BIPV coating. And before we leave, I would like to advertise a little bit on our next webinar series. So our next iclimabuilt webinar series will be on the topic of innovation insulating materials. And the date will be on Wednesday, the 8th of November, and the time at 10 to 11:30. And the speakers are, we have 3 invited speakers: Miguel from RISE, Agnes from Setma from Italy, and Michelle Fenex from Switzerland. So, and if you have any question regarding to webinar series, you can contact me. Here is the info, and also follow us on iclimabuilt.eu. We have social medias on Facebook, Twitter, and Instagram. So thank you very much for your attention today, and we hope to see you for the next webinar series. Thank you.
Thank you very much.
Thank you.